Welcome. Today we are exploring the Doppler effect. But first, let's define a wave. It's a disturbance that transfers energy through matter or space. Mechanical waves, like sound or water ripples, require a medium, like air or water, to travel through. They physically displace particles as they move. Electromagnetic waves, however, don't need a medium. They can travel through the vacuum of space. Visible light and radio waves are perfect examples. Every wave has key properties. Amplitude is the maximum displacement from rest, while wavelength is the distance between consecutive crests. Period is the time for one complete cycle, and frequency, measured in hertz, is the number of cycles that pass a point per second. These are linked by speed. The wave's speed equals its frequency times its wavelength. Change one and the others adjust to maintain the balance. When a source or an observer is moving relative to each other, the detected frequency by the observer is different from the frequency emitted by the source. This is known as Doppler's effect. The increase or decrease in frequency will depend on the direction of motion. To use equation for Doppler's effect, let's define our glossary. Fs is the frequency emitted by the source, and Fd is the frequency detected. V is the speed of sound in air, about 340 meters per second. Vs and Vd are the velocities of the source and detector. As the change in frequency depends on direction of motion, we need to specify the direction. Crucially, the direction from the source toward the detector is considered positive. Moving opposite to the sound's direction is negative. Here's the relationship. The detected frequency equals the source frequency times the ratio of the relative speeds of the detector and source. Example time. A car siren emits 400 Hz while moving at 20 meters per second toward a stationary person. Since the source is moving towards the observer, the detected frequency will increase. Let's calculate it. Plugging in the numbers, V-D is 0, V-S is 20. We get 400 times 340 divided by 320. The detected frequency is 425 Hz. As expected, a higher pitch. This also happens with light. When a star moves toward us, its light shifts to the blue higher frequency end, away, and it shifts to the red. We use this for everything. Police radar guns, tracking weather patterns, and even proving the universe is expanding. Before we wrap up, let's clear up a few misconceptions. The Doppler effect does not change the speed of the wave. That depends entirely on the medium. Also, don't confuse it with a change in volume. It's a change in frequency which we perceive as pitch. From sirens to stars, the Doppler effect helps us measure the moving world. Thanks for joining me for this physics breakdown. See you next time.